Hi, everyone. My name is Will Creighton. I'm a sixth-year PhD student at Stanford, and my research combines PL theory and cognitive psychology to design better programming tools for people. And this paper is part of my thesis work done under my advisors Pat Hanrahan and Manish Agarwala, and also in collaboration with Marco Paccignani. So the motivation for this work was to build a practical program slicer. Let me show you what I mean by program slicing. So a program slicer is a tool where a user clicks on a particular variable, and the tool shows the subset of the program that could influence that variable or is influenced by that variable. And what you're seeing is the actual tool that we built. It's a VS Code extension that can take any Rust program and interactively visualize the slice of whatever is under your cursor. And I call this practical because it just works. You can pop open any Rust code base and slice it any way that you want. So this talk is about the analysis underlying this slicer. And it is also the story of how I built a program comprehension tool and ended up in the security session at PLDI. And that is because the same technique underlies both program slicing and information flow control, which is information flow analysis. So to set up this problem, let's start with what information flow is and why it's difficult to analyze. So we say that some variable x has an information flow to y if x can influence the value of y, or that x can cause a change in the value of y. And as a running example, we'll use this C++ function. This function copies all of the elements from one vector v to another vector v2 up until some index max. And here we can say both v and max have an information flow to v2. Because v goes from v to v.begin, which goes into x, that goes into the dereference of x, that goes into pushback, that goes into v2. Whereas max affects how often this break statement gets run, which is going to affect the number of times pushback gets executed. Both of these are instances of information flows that we would like to detect. And so the challenge is, how would you write an analysis that could deduce those flows? And for now, let's focus on how v here influences v2 here. For that, we need to deduce a few key facts. The first thing is when we do x parentheses v.begin, this creates an iterator, which is a pointer to v. So when we dereference it here, we have to know that that's pointing to data within v. This is sort of the pointer problem of knowing what x points to. And second, when we call v2.pushback, we need to know that that mutates v2 with x as input. So I'll call that the mutability problem, knowing what pushback will change. And as you saw earlier in the demo, we want to be able to drop into an arbitrary code base and analyze a given function within a matter of seconds. And so under that standard, here's a few solutions we can immediately rule out as impractical. So one is we could just say no programs with pointers and mutation, but that is how the world works. Another is to say have the user annotate functions with their effects. But people don't want to do work just for the tool. Another is to run the program and see what happens, a dynamic analysis, but this can be both slow and unsound without complete code coverage. And so finally, we could look at the source code of our dependencies, like the definitions of begin and pushback, and see what they're actually doing, but libraries don't always ship source code, and also whole program analysis can be quite slow. So in a sentence, our goal is to build a modular, static, information flow analysis for an imperative language that requires no additional annotations. And the core insight of our work is that memory safety analysis has to solve similar problems as information flow, and ownership types are a mechanism for modular, static memory safety analysis. Therefore, we can repurpose the existing ownership annotations that programmers are already writing in languages like Rust for information flow. So now let's dig into the specifics. First, we're going to talk about memory safety. And as an example, I'm modifying the C++ program you just saw to not only copy elements, but remove them from the input vector. The only change is this new line, v.erasex, that deletes the x iterator element of v, which this program was fine before, but dangerous now. If you run it with the right input, you'll get a segfault because this code has two simultaneous references to the vector v, which are the iterator x and v itself. And you allow v to be mutated through one of those aliases, leading x to point to deallocated memory. More generally, this means any tool which checks a program for memory safety needs to understand pointers and mutation, which were exactly our two problems. So that brings us to Rust. Here's the same C++ program, but written in Rust. It has the same arguments, the same vector v2, a slightly different way of creating an enumerated iterator, a push onto v2, and then a deletion from v. But the main difference is when I ask Rust to compile this program on the bottom, I will get the following error. It says, cannot borrow v as mutable because it is also borrowed as immutable, correctly observing that v.iter creates a pointer to v and that v.remove tries to mutate v, successfully identifying our memory safety bug. But in order to bring this back to information flow, we need to understand how the borrow checker actually generated this error message. And so here we arrive at the concept of ownership types. So ownership types boil down to two language mechanisms, which I've illustrated here by expanding some syntactic sugar. Specifically, every pointer type and pointer expression is annotated with two things. The first is a lifetime, written as tick alpha, that indicates how long the pointer will live. The second is a mutability modifier, either mute or no mute, that indicates whether the data under the reference can be mutated. And it's worth noting that unlike C++, this is a transitive modifier, so nothing accessible through a no-mute reference can be mutated. And so given these mechanisms, the borrow checker works like this. First, the compiler asks, are there two pointers to the vector v with at least one being mutable? And here we can see two expressions. There's one with the lifetime beta on line 4 put into vec_iter, and then there's one with the lifetime delta on line 8 that's put into vec_remove. And that second one has a mute modifier. And the reason it has to be mute is because of the type signature of the method involved. The vec_remove method says it only takes a mutable reference as input, therefore it must be mutable on line 8. The next question the compiler asks is, do the live ranges of these two pointers overlap? Like, what do their symbolic lifetimes actually mean? And so here, the live range of delta is just line 8. It's only used there. The live range of gamma, the iterator x, is the entire for loop, because it's a for loop variable. But then it's not obvious what the live range of beta that we passed into iter should be. And the answer is that it is the same as gamma. And the reason for that, again, comes down to the type signature of the method involved. The type of iter uses what's called lifetime polymorphism. So this variable tick a indicates that the lifetime of the input vector, self, is the same as the lifetime of the output references. So by only using the type of iter, we therefore know that beta is equal to gamma, therefore that beta and delta overlap because the line 8 is in both sets, and so we have these overlapping pointers where there's at least one that's mutable, therefore raising the error. That's how the borrow checker works in Rust, using ownership types to check memory safety. And going back to our criteria, the point is that this example shows that it is a modular static analysis for an imperative language, and the only downside is that it requires configuration from the user. The person who wrote, for instance, the vec_remove type signature had to specify that mutability modifier. But the point is, once these annotations are there, then we can return to information flow. So let's go back to the original copy to example. This time it's in Rust. And remember that the challenge was to determine that there's an information flow from v to v2. And we can solve the two problems we had of knowing that x points to v and that push mutates v2 by using these two mechanisms. For the pointer problem, we know that x points to v because x shares a lifetime with v. And more generally, we can say for any pointer p that has a type and tick at, that the points to set from p can be derived solely from the lifetime. And I haven't described the construction of this set, it's in the paper, but this is an important aspect of how we do a pointer analysis. And then for the mutability problem, we can say that vec push mutates v2 because it takes a mutable reference as input. And the general rule is that if you call a function with some arguments, we will say all of the inputs have an information flow to only the mutable pointers in that argument. So we know, for instance, that push mutates v2, while iter does not mutate v. And that's pretty much it. Like, once you get how ownership types work, the resulting analysis is a set of fairly straightforward approximations based on these types. There's some subtlety around issues like field sensitivity and strong versus weak updates and stuff I am happy to chat about later, but this is the core technical insight. And so now, given this analysis, we wanted to evaluate it in two ways: its soundness and its precision. So by soundness, I mean if an information flow exists in a program, our analysis will find that information flow. And so we made a formal proof of soundness with a couple of tricks. First, we leveraged some work called Oxide that formalizes the semantics of safe Rust, and then we embedded what's called a dependency calculus into the Oxide type system. So here, this is the base Oxide typing judgment in black with the added dependency calculus in red. Then we extended all the Oxide inference rules with the corresponding dependency analysis. And finally, we could formulate and prove a non-interference theorem about the analysis, showing that it is sound in the safe subset of Rust. Then we looked at precision. So like most static analyses, our tool is imprecise. Just as one example, in this program, we create a vector v, and then we get a mutable reference to an element of v, x. But we don't actually mutate x, so line 2 has no effect on v. But the issue is that this function has to take a mutable reference as input to sort of pass off that permission to the output pointer. And the rules of our analysis said, because getMut takes as input a mutable reference without looking at its definition, we have to assume that that line mutates v. And therefore, our assumptions don't match reality, and there's an imprecision. And so, more generally, to understand precision, we have to answer an empirical question. How often do Rust programmers write code fitting these kinds of patterns? And we investigated that question in 3 steps. First, we created a whole program variant, or non-modular variant of our analysis, which basically, whenever it sees a function call, rather than just looking at the function's type signature, it would recursively analyze the information flow when the source of the function was available. So a lot slower, but more precise. And it would, for example, recognize that getMut does not mutate v. We took these 2 analyses, modular and whole program, and ran them on every variable in every function in 400,000 lines of code taken from popular Rust code bases. So then for any given variable, we could say, what are the information flows computed by one analysis versus another? And the basic finding is that in 94% of cases, they were exactly the same, that the modular analysis produced the same result as the whole program analysis. Which, another way of looking at it is that given a program written under the discipline of ownership types, you don't lose much information by only looking at the type. Like if a function says it's taking a mutable pointer, it is probably going to mutate that object. And so in the end, we've built what I think is a fairly practical system for information flow analysis called flowistry. As I showed in the beginning, we've used this analyzer to build a program slicer, which is in active use by a non-zero number of Rust developers. We have 1,500 downloads of the tool and 1,000 stars on GitHub. And I think there's a ton of exciting research directions here, no matter your interest. So if you are into HCI like me, we have some ongoing research about the human factors of the slicer, like when and how it can be useful for tasks like debugging. If you are into security, we are exploring some collaborations right now to build an IFC system using flowistry. If you're into static analysis, there's a lot more work in building this up to handle the full generality of Rust. I emphasized our analysis is sound for safe Rust, but there are escape hatches in the language where information can flow in ways not detectable by us, like calling a C library or writing to a database. And I'd love to collaborate on making this analysis as robust as possible for real-world settings. And that's it. Happy to take any questions. Thank you.
Thank you, Will, for the great talk.
Thank you so much.
I was just wondering if you could go back to the previous slide when you said there are 94% of like the matches.
Yeah.
What exactly were the cases that didn't match? Like, was it just people annotating it poorly? Like, I don't know.
It's a great question. So we have a detailed breakdown in the paper. This is one such example where there are use cases where you need to take a mutable pointer so as to say pass off that permission, but then you don't use it. And there are other forms of imprecision. Like I mentioned, we have to assume, without looking at the definition of a function, that all of the inputs were relevant to every information flow. But it might be the case that, if you take x and y and then some mutable pointer z, only x was relevant to z and not y. Y was used for some other purpose. And so these kinds of imprecisions arise, but it just sort of turns out that they're not that significant in practice, that the sort of basic approximation seems to be pretty good.
Okay, thank you so much.
Yeah.
Oh, thanks. Good talk. So I was just wondering, how essential are lifetimes to this analysis? So you could imagine redoing a lot of this analysis just with a system without ownership and borrowing, but with mutability annotations on fields of tables.
Yeah, great question. So we also did an ablation analysis, which is also in the paper. I won't deeply interpret these graphs, but basically what we did is we simulated our information flow analysis as if we didn't know anything about mutability modifiers, like we assumed every pointer could be mutated, and as if we didn't know anything about lifetimes. So all pointers of the same type were assumed to be aliases. And we found empirical evidence that when you sort of don't allow yourself to use that information, the average number of information flows you're detecting will go up by like 50% or so on. There are significant increases in the number of flows or the size of your slice that you find when you ablate away these capabilities. So, and that's even on a Rust code base, which is already designed with these things initially and probably has fewer pointers than a corresponding C code base. So I think there's fairly good evidence to suggest that these mechanisms are actually important. If you try to do the same thing for an arbitrary C++ program, like a similar kind of approximation, it would likely be much worse.
Hi, thanks for the nice talk. I was wondering, what if I don't use unsafe code myself, but I use some of the interesting building blocks I get from the standard library, like cell or mutex or something? Are there, which can like have interesting flows because now there's aliasing problems, all of that. Does your tool detect those, or does it become unsound with those types?
So you're correct in that any primitive that is on some level built on unsafe code cannot be within our system internally consistently proved to be, or we cannot soundly analyze such an API or be guaranteed to do so. A good example of this is a mutex. So if you use a mutex, mutexes in Rust are specifically designed along with atomic reference counted pointers to not share lifetimes between two pieces of data, or two references to the same data that are protected by a lock. They can't share lifetimes because that's the only way Rust allows you to split that across multiple threads. And so we cannot detect when going through an arc mutex that one mutation is relevant to another. And more generally, right, interior mutability is the most common name for this sort of pattern. And this is like an open question, whether we just need to annotate certain kinds of primitives or what exactly the right solution is there. Like ideally, this sort of approach can reduce the space to say, only these sorts of things we know like that have interior mutability or that are tainted by interior mutability we need to do some sort of more conservative analysis on, or we need to ask for more annotations from the user. But that's one of our open research questions right now. Yeah.
Hi. Thanks for the great talk. Really interesting work. My question is sort of Alan's question, but in reverse. So which is that in theory, it seems like one could have pointers that have the same type and the same lifetime, but are not aliases of each other.
Yes.
And I'm curious if you saw any of the imprecision resulting from that, and if so, how much of it?
Yes. So this is another thing I've been working on as we apply this to more realistic code bases. There are cases where two pointers are asserted to have the same lifetime, and therefore and have the same type, and therefore we must assume the alias, even if they don't need to for fundamental reasons, or that's just solving some other random borrow checker issue. And so that's that is an imprecision that arises from lifetime-based alias analysis. I think there's another sort of open direction of research here of how to make just the pointer analysis part of this more precise. We kind of tackled the vertical, but there's lots of interesting subproblems along the way. Another thing I'll mention is that more broadly, an interesting phenomenon here is how anytime you improve the borrow checker, like you make life better for a Rust user, you're also making flowistry more precise. That, for instance, non-lexical lifetimes allows us to make more precise assumptions about which lifetimes don't overlap and therefore which pointers can't alias than in the earlier system of lexical lifetimes. And so I think there's an interesting interplay here where if you improve the type system to, say, try and reduce the number of borrow checking conflicts, you'll also find benefits for this kind of downstream static analysis like flowistry. So my hope is kind of joint efforts there will also help reduce the imprecision in these kinds of lifetime-based pointer analyses.
So as a follow-up to that question, I think I've noticed that people who are less experienced with Rust tend to tie more lifetimes together than necessary.
Yeah.
Have you done any research on if that affects flowistry's precision, like for less experienced users?
Yeah, so we don't have a sense of, like the code bases we analyzed in our data set were very sort of production ready. So we didn't have a huge data set that's representative of every skill level in Rust. And this is something I think would be interesting as well, is how different code styles impact the efficacy of this particular style of analysis. I mean, my initial sense is that Rust tends to infer lots of lifetimes and most novices try to just stay away from it, or they go back to interior mutability, at which point you're in the unsound territory. So that's probably the deeper issue, is just if you have to wrap everything in RC ref cell in order to get your code to work, then our tool is not necessarily going to be as useful. And so, trying to make lifetimes as ergonomic as possible, and then also inferring as many of them as possible and avoiding unnecessary restrictions on them is both good for those novices and going to make the tool better. Yeah.
Okay, so let's thanks Will again. Thanks for the great talk.
Thank you very much.